Welcome to the Crazy Hat Chemist. So another video here, and we are starting a new unit here today. We are working with acids, bases, and titration problems relating to acids and bases. So let's get started with a little introduction. Bam! So today we're talking about an introduction to acids and bases. A lot of information in this unit video right here. So let's move on. So here are a lot of different real-world examples of which you would experience on life dealing with acids and bases. This is a pool right here, and in a pool we're going to be adding muriatic acid, sometimes some sodium carbonate, and of course some liquid chlorine or bleach tablets of some kind. Okay? Citric acid in lemons, citric acid in oranges, but also ascorbic acid in oranges. There's rhubarb with, what is that? Oxalic acid. That's right, oxalic acid. And we have in Drano or other drain cleaning products, we have sodium hydroxide, sodium hypochlorite, sodium nitrate, sodium chloride, and aluminum. This is Clorox bleach, and this is sodium hypochlorite. This is malic acid in tomatoes. And magnesium hydroxide is something that we use for calming our stomach if we have an upset stomach. Okay, there's fish that has a bunch of different acids in them, okay? And hydrangeas. Hydrangeas are a really cool flowering plant, okay? In acidic soil, that means in acidic soil, you can make them blue in color, the flowers. And when they're in a basic soil condition, they are going to be red in color. So you can either add acid or base to the soil and change the color of the hydrangeas depending on which color you want. A super cool flower and plant. Okay, this is lye or sodium hydroxide. I don't know if you've ever heard, but you know, people would put a long time ago lye around houses or maybe around people that were passed away or something like that, so the smell wouldn't be so bad. Okay, this is borax, okay, and that has an acid, which is boric acid in it. Okay, and then maybe you've seen this placard somewhere, but this placard is letting you know that acids and bases, okay, are dangerous and they are caustic, okay, and they can cause corrosion either to metals or your body itself, okay, and that causes chemical burns. So that's why you want to make sure that you're wearing goggles for one thing anytime you're dealing with acids. Certainly gloves or working within the same with safe conditions. All right, so we're going to keep on going. We got a lot to cover here. Here's a diagram of an acid rain, and we have SOx and NOx essentially is what produces acid rain. So I want you to look at this here. We have a variety of different sources of things that cause acid rain. Okay, so production facilities of chemical plants, just industry in general produces things. We have cars that produce gases. Okay, and here are some of those gases. So sulfur dioxide, that's SO2 plus oxygen in the environment will form sulfur trioxide gas. That sulfur trioxide gas will now interact with the water in the environment and produce sulfuric acid. That sulfuric acid in the atmosphere will now come on down as acid rain. Okay? And then NOx, SOx and NOx, right? SOx and SOx and NOx, right? And nitrogen dioxide plus water will form nitric acid and nitrous acid. Those two acids, nitric acid and nitrous acid, will also come down in the form of acid rain as well. And it will destroy our environment in a variety of different ways. It can kill plants, kill trees, okay, kill lakes, rivers, streams, and creeks, in decreasing the pH of that system such that the plants and animals do not exist in those systems. Okay, if we have any sculpture work or something like that that is made out of certain kinds of rocks like limestone, then they will deteriorate very quickly over time. Okay, here are some basic characteristics of acids and bases that you need to know. Number one, we're going to cover acids, then we'll cover bases. Okay, acids are electrolytes. Okay, they have a sour taste to them, and hopefully you've tasted like a lemon or a lime or something like that. That's a sour taste. Why is it a sour taste? Because it's an acid. Okay, it turns litmus paper into red. Phenolphthalein is colorless when it's acidic, and acids react with metals to produce hydrogen gas. They react with hydroxide bases as a neutralization reaction, and they react with carbonates to produce carbon dioxide. Okay? Excess hydrogen ions, i.e. H plus ions, let you know that there's acid in that solution. Okay? All right, now bases, here we go with bases. They are also electrolytes. An electrolyte now is something that conducts electricity, and I'm going to cover that in much more detail in another video. Okay, they are bitter or caustic in taste, so bitter taste. Okay, they turn litmus paper to blue. Okay, they are slippery or soapy feeling, and in fact, many of the bases, you're experiencing many bases when you actually wash your hands with soap and water because that soap is slippery. Okay, bases react with acids to form a neutralization reaction. And fats to form soaps. This is how we make soaps. I don't know if you've ever made soap before, but you use a base and a fat and you got yourself a soap. Excess hydroxide ions, that's OH ions, that means that you have a base. Okay, so we got a delineating line between acids and bases right here. Okay, here are multiple different definitions of acids and bases, and you need to memorize these. So an Arrhenius acid is one that contains an excess of hydrogen ions. A Brønsted-Lowry acid is a proton donor, and this leads to the concept of conjugate pairs that we're going to discuss in just a moment. A Lewis acid is an electron pair acceptor. So the question is, why are there so many definitions of acids? Okay, it's because not one definition will fit all the different categories. There is no universal definition for acids or bases. So depending on the type of acid and the way it reacts with different things, then we have a different definition for an acid. But they are all acids. Okay, so here's an example, just a very generic example of an acid, and that's HA, generic example of an acid, plus water gives me hydronium ion, that's H3O1+. I'll talk about that in a little bit too. And the conjugate to that acid, which is A-1. Okay, we can shorthand note this reaction as just HA produces hydrogen ion and the conjugate to the HA, that's the A-1. Okay, an Arrhenius base is one that contains excess hydroxide ions. A Brønsted-Lowry base is a proton acceptor, and a Lewis base is an electron pair donor. Notice that they are exactly opposite that of acid. So as long as you know your acid definition, you know your base definition. Or if you know your base definition, you know your acid definition. Hopefully that's pretty simple. Okay, and here's an example of a reaction with a base. We have A-1, an anion, plus water gives me an HA. That's actually going to be an acid, and a hydroxide ion. Notice that there's hydroxide ions that are on the production side, which is on the product side, as opposed to the acids, which produce hydrogen or hydronium ions. Okay? Okay, I want to make sure that you never do this, and this is very important that you pay attention to this. Never trip on acid, especially like what I've been doing right here. That's very problematic. That's concentrated nitric acid that I'm tripping on. That's not good. That's an oxidizing strong acid. Okay, we'll talk about strong acids a little bit later. Okay, conjugate acid-base pairs. Okay, so one of the theories of acids, definitions of acids led to conjugate acid-base pairs, okay? And from this Brønsted-Lowry definition of an acid, where an acid is a proton donor, that is a hydrogen ion donor, okay? And the Brønsted-Lowry definition of a base is a proton acceptor. So notice it's a proton donor, a proton acceptor for the Brønsted-Lowry. Okay, this leads to the connection between the two forms of what are called conjugate pairs with the hydrogen ions. One's accepting, one's donating. Okay, and so we're going to take a look at this equation here. On the reactant side, on the left-hand side, we have HCl, which is hydrochloric acid because it's aqueous in solution, plus water, that's liquid. Those are on the reactant side. On the product side, I have a chloride ion in solution, and I have H3O1+, that's called a hydronium ion. Okay, the connection between the reactant side and the product side is as follows. What you need to do is find something that is similar. In this case, it's a chlorine. So there's a chlorine on the reactant and a chlorine on the product, and those two are connected together as a conjugate pair. There's either a plus or a minus of a hydrogen ion. Okay, the one with more hydrogen ions is the acid, the one with fewer hydrogen ions is a base, and it's only a plus or a minus of a one single hydrogen. Okay, and here's the other set of conjugate pairs, that is water and the hydronium ion. Okay, water in this case is a base and the hydronium ion is an acid because the hydronium ion, H3O+, has one more hydrogen than the base of water does. Okay, notice that this reaction here, on the reactant side, I have an acid and a base, and on the product side, I have an acid and a base. Okay, this is going to be a telltale characteristic. On the reactant side, you will never have an acid and an acid or a base and a base. Okay, one of them will be stronger and overwhelm the other one, if you will. Okay, and since hydrochloric acid is such a strong acid, its conjugate is a very weak base. Okay, and then therefore the water is going to be a strong base in comparison to the hydronium ion, which is an acid. Okay, all right, here's another example here, and now we're going to look for conjugate pairs. Now, in finding conjugate pairs, we want to find something that is the same, an element that is the same on the reactant side and on the product side. So what is the similar element? Well, it's a nitrogen, and hopefully that's easily seen. So I have NH3, which is ammonia on the reactant side, water on the reactant side. Then on the product side, I have the ammonium ion in solution and the hydroxide ion in solution. So the conjugate pairs here that are really easy to differentiate here is that the ammonia and the ammonium ion both have nitrogen. Okay, the one with more hydrogens is the acid. The one with one fewer hydrogen is the base of the two conjugate pairs. Then the other conjugate pair, okay, is going to be the water and the hydroxide. Again, there's an addition or subtraction of only a hydrogen ion when you have conjugate pairs. So the water in this case has one more hydrogen than the hydroxide, therefore it's going to be the acid and the hydroxide is going to be the base. Okay, so I want you to see here, and I'm going to cover this in just a moment, that water can be both an acid or a base, and I'm going to let you in on a little secret that's called amphoteric. Okay, and the strong always push the weak. That is, hydrochloric acid is a much stronger acid, okay, than the acid on the product side, which is the hydronium ion in this case. Okay, so we're going to come back to that with strong and weak a little bit later. So amphoteric substances, and I kind of alluded to this with the previous slide with water, but I'm going to show you here what this is. An amphoteric substance is one which can behave as either an acid or a base. It really is a comparison thing. So, am I strong? Absolutely. I am very strong compared to a baby. Okay? Am I weak? Yes, I am very weak compared to Arnold Schwarzenegger in his prime. So, am I amphoteric? Yes, I am. I am amphoteric. Okay, I can either be strong or I can be weak, and it depends on what you compare me with. Okay, and so the same thing happens with some acids and some bases. So some metal hydroxides, aluminum, zinc, chromium, are amphoteric. Okay, and then some other examples. So hydrochloric acid, I gave you this example previously. Here are my conjugate pairs. That's a base, because the hydronium ion has one more hydrogen ion. And here I gave you this example as being an acid, where the water is an acid. So that means that water can be amphoteric. It is behaving as either an acid or a base. Okay, all right? Hopefully that makes sense. And then getting back to the metal hydroxides, zinc hydroxide plus hydrochloric acid. Now, because hydrochloric acid is such a strong acid, therefore the zinc hydroxide must therefore be a base. Okay? And then zinc hydroxide in comparison to sodium hydroxide, and sodium hydroxide is a strong base, therefore the zinc hydroxide must be an acid. So zinc hydroxide or other metal hydroxides, okay, other than group 1 or group 2, can behave as either an acid or a base. That is, they are amphoteric, just like water is amphoteric because it depends on what you compare it to. Okay? Hopefully that makes sense here for you. Now I want to get into the hydronium ion, and I did talk about the hydronium ion multiple times, but I didn't tell you what the hydronium ion is. So a hydrogen ion, that is an H1 plus ion, is a bare proton and does not exist by itself in water. That is, in aqueous solution, that is. So in water, the hydrogen ion combines with a polar water molecule to form a hydrated hydrogen ion, which is called a hydronium ion as H3O 1+. Okay, so this is the reaction. You see water on the reactant side is H2O. You got those two lone pairs. Okay, if there is a hydrogen ion, a bare proton in solution, then it immediately interacts with this water molecule to form the hydronium ion, which you should see on the product side here. Okay, fantastic. Okay, so a note on some notation when you see things in a textbook. Okay, so you should see that when we write the word with, that means we're writing H3O 1+. But we can write an abbreviated version of with, and that is a W with a slash. Okay, so a W with a slash is not really the true form of when we're writing with, and our English teacher would certainly not accept that in an English essay. So the W with the slash is equivalent to the hydrogen ion, which is a bare proton, but we really assume that that W with the slash is the full word, like the hydrogen ion is the same thing as the hydronium ion. They are different, but anytime you are dealing with something in solution, it is most certainly always the hydronium ion, but many times in chemistry, we shorthand note that as just a hydrogen ion. Just so that you know, if it's in solution, it is a hydronium ion and not a bare proton. Okay? I am the Crazy Hat Chemist. Hopefully you enjoyed that video. And I want to thank Jordan very much for giving me this hat. She's awesome. I had her as a student from many, many years ago. Give me a thumbs up if you like that video. Subscribe to my YouTube channel and find my cool website online. I've got so much information. I got so many videos for your learning of chemistry. I'm going to see you next time. Bye for now.